Okay, yeah. I graded your first video project. I enjoy watching them. Okay, I really enjoy watching them. To be honest with you, the class like this, I never see your face to face, right? So that's the opportunity for me to actually see everybody. And you talk in front of camera just like you're talking to me. I like it. I enjoy like that, working with you, and this is probably the only opportunity we can see face to face, right? You can always see me every time I turn on my video, so I can see you now. So good. Okay. First of all, the grading. This class 85 is A, 75 is B, 65 is C, right? Overall. So in each project, in each quiz, it also follow that scale. So I think if you score 85 or above, it's excellent. Okay, it's an excellent project you did. If you score 75 or above, it's a good project. Okay, so you did a good job. So just remind you, okay, that's our grading scale. It's not 90 and 80 and 70. So we're a little bit, lower, right? It's 85, 75, 65, and 55. Okay. This is grading. I think most of you did good, especially as a first project. Yeah, most of you did a good project, and you conduct the experiments and you prove the heat conduction, right? That's the goal of the project. Okay, a couple of things I want to mention here. Okay, there are two levels of the verification, okay, for doing any experiment. Two levels of verification. One is to verify for example, the heat conduction exists. Okay, for sure, of course. If you do any experiment, you have to prove that it exists, So, and also the heat transfer from high temperature to low temperature through a material, something like that. You prove that it exists. Everybody did, okay? Everybody did. So from your experiment, I can clearly see the heat conduction exists in reality, okay? But that's a base level, okay? The second level, which is the higher level, which separates some good project with the other project, is the second level is to verify the equation. First of all, you verify, this heat transfer exists. Then we have equation, from, previous people developed, experimented, and they observed, they discovered, and they concluded with a mathematical equation. Okay, so that's the second level of verification. You try to prove the equation is correct. In that sense, your Q equals to negative Ka dt dx. Okay, so you basically try to prove that equal sign between the Q and the expression in the right-hand side. Okay, that makes sense? So you cannot just say, hey, I calculated, I measure the temperature, and I know the conductivity. I calculate the negative Ka that dt dx. So what? That's the Q? No, you haven't proved it, that's the Q. Okay, that's the expression. So you have to prove that's exactly actually the Q, the heat transfer rate or the energy generation from the source. Okay, so you have to use another method to find the Q. Okay, then you find out, hey, the Q value I find out, for example, you can find out from your heater. Usually the heater have the wattage, right? Okay, so you can have the current and a voltage or something like that. You can find the wattage. Assume that total heat being generated and being transferred into your material. So that's the heat transfer rate. Okay, that's not exact. I know there's some losses, sure, but that's the process. That's the procedure you take to verify an equation. Okay, and you cannot just say, hey, my temperature gradients are like this and times K times the area. Okay, that's my heat. Oh, I did a verification. No, you didn't. Okay, you just measure the temperature gradients times K times A, basically. That's what you measure. What is that? I don't know until you prove it. Okay, that's equivalent to the energy generated from the source. Then you prove the equation. Okay, that makes sense. I think many of you did well, did very good on that aspect, but some of you didn't clearly show me the verification for the equation part. So I just want to mention it here. okay, to emphasize it. Hopefully in the future project, you can do that a little bit better. Okay, that makes sense? I hope you use this method actually to basically, if I give you a test, so basically you just apply the equation to solve this problem. But now you're actually doing this problem. So you apply the equation, in the process. So I hope you learn during this process. I hope it's a more effective way to learning. Okay, so the only limitation is sometimes we cannot do very complicated projects, complicated experiments. We don't have the availability of the equipment, apparatus, whatever. So some of the complicated problem we cannot test or experiment, but that's all right. Okay, I think we learn the concept, learn the basics. It's very important too. Okay. So that's what I want to say about the experiments. But I think you did good. From looking at your score, you can tell. Okay, I think most of you, did very good, above good, right? So excellent and good. Okay, so I hope you keep on the good working and do better and better. Okay, and eventually you learn the knowledge. Okay, so that's the goal. So reminder, the second experiment is due tonight, right? Okay, so, okay, let's continue on chapter. We have chapter 2, we have one topic we haven't covered. It's the thermal contact resistance of the fin. Okay, so that's also important, very practical. Okay, theoretical world, people, sometimes ignore those small details, but in the reality, in the real application, in the practical application, we really need to consider those small details. Okay, so let me share my screen. Okay, here we go. Okay, hold on. Okay, thermal contact resistance. What is that? So here we're talking about the fin, right? You install a fin to increase heat transfer. When you install it, when you attach it to some structure, there's something in contact. Okay, either glue or either whatever material in contact. Or sometimes you're not perfectly contact on the surface. Then you have gaps, you have, air trapped inside, in between the contact. Okay, plus the surface is not smooth. The surface, whatever material, the surface, it cannot be really, really smooth. It also has a roughness. If you use a microscope to look at the surface, it's all like mountains, okay? Micro mountains, okay? So for two surfaces in contact, if it's not perfectly smooth, mountain plus mountain, you have more mountains, okay? So that you definitely have some gaps in between two surfaces, which will trap some air in there, okay? So, air has a very bad conductivity, right? The conductivity is really, really small. So it's not a conductive material, air comparing to whatever solid material, I guess, because most of the solid material has better conduction than air, okay? So if you have air in between, two surfaces, really it will decrease the heat transfer, okay? So it contributes some resistance, okay? Let me send you a figure. I think it's good to look at the figure 2.15. Let me send it to you through our group. Please take a look, and then when we talk about this figure, okay, please open your phone or go into our group. You see that? Did you see that picture? Figure 2.15 on the textbook. Okay, page 58. Okay, so that's the temperature distribution between two materials. Okay, so you have two material in contact. Okay, look at the temperature. The heat transfer is from left to right. By the way, everybody, are you looking at the figure? Can you see that figure in the group?
Yes, sir. We can see it.
It's still loading a little bit.
Oh, it's still loading. Okay. Okay.
All right, there it is.
Okay. Good. See, you have two material A and B. Okay, A and B, two material. The length delta XA and delta XB for two material, right? When you're in contact, okay, the heat is from transfer from left to right. Okay, so that's the situation. So now you know temperature linearly decreases in the material. Conduction, Ka, you know, heat transfer rate is what Ka dt dx, right? So it's first order derivative, so it's linearly change, okay? So it's decreasing, straight line, right? From T1, T1 is the temperature at the left, which is the high temperature, right? T2 is the temperature, T3 is the temperature at the outlet, right? Like at the end, so it's a lower temperature, high to low. So temperature in material A is decreasing, straight line, linearly decreasing, okay? Temperature in material B is also decreasing linearly, but for the contact region, because of the contact, okay, it's not perfect. You have a sudden temperature drop, okay, on that contact point. You know, because that's a resistance there, right? So, but don't get me wrong. Some of you, when I look at your project, heat conduction, you have multiple materials, okay, conduct each other. You said, some of you just said the heat is being lost or something. So, but see, in this situation, if the outside surface is insulated, it's a 1D conduction, then no heat lost. Although the temperature drops here, it's not lost. Its temperature decreases because of the higher conductivity, but it's nothing lost there. Energy is not, it's not lost. That makes sense? The heat transfer rate is the same. It's keep constants going through the entire structure, entire solid material. Okay? It's not lost due to, don't say that. It's not lost due to the, for example, contact. No, it's no. Temperature drop due to the contact. But the heat is still there. The heat transfer rate, heat flow is still there. Okay? So that's the physical behavior, temperature distribution inside this two A and B material with the contact. Okay, so there's a sudden drop here. It's, let's say, from T2A to T2B, right? Go through this contact region. So it dropped a little bit. So how do we mathematically describe it? This is a review, okay? So do you know how to calculate the heat transfer rate for the, see, that's the basic, right? Some of you still, I think, is still confused. So that heat transfer rate, you have in this whole system, you have only one heat transfer rate. It never changed. So if you can find it from certain ways, a certain region, you can find the Q, that Q is the same in the entire system. Okay, that's very important. So for this system, you can find, since you know T1 and the T3, okay, you have three pieces in that system, right? A and B and the contact region. So you can easily use the beginning and the end to find out the heat transfer rate, right? That heat transfer rate will be the exactly same heat transfer rate going through that contact region only. Okay, does that make sense? Okay, so you can say, hey, I can say this how to say, the T1 and the T3, right? It's beginning and the end. So it will be Ka. If you use positive Ka, okay, so let's not use Ka. Use thermal resistance form. Okay, that will be easier to explain. I like a thermal resistance form. Okay, so you will use the beginning and the end. Okay, beginning and end temperature. So T3 minus T1 minus T3, I'm sorry. T1 minus T3 divided by what? You have 3 items, right? Thermal resistance of RTH of A plus the thermal resistance of the contact, let's say C, plus the thermal resistance of what? Of B. I want you to really 100% memorize this. This is the way you calculate the heat conduction, convection, combination problems, whatever. Okay, so this equation is much easier than to remember the details. Okay, so starting temperature minus ending temperature divided by all the resistances. Okay, so the resistance of A and B are easy. They're conduction, right? Anybody remember? Don't look at book. See if you can memorize.
Is it
Delta X over KA?
Yes, delta XA over K. Do they have the same? Let's say different K. How about that? A is the same. Okay, seems like from the drawing, A is the same. So thermal resistance, that's good. Okay, you remember. That's great. Then you don't have to, every time you solve a problem, you don't have to go and open the book and find out the equation, right? It will get you less frustration if you memorize those things. So thermal resistance of B is the same thing, right? Also same form. Okay, so if you remember, no problem, we solved it. So what is thermal resistance of the contact? Okay. We follow the heat convection fashion of the heat convection equation. Remember, heat convection equation was Q HA delta T, right? So your thermal resistance of the convection will be 1 over HA, right? Okay, is that right? Is that what we remember for the convection? So in this H is the convection coefficient. You know, this convection is not as strong theory as the conduction. That's why we don't know what to do. Basically, they just make up this equation, H times A. They put a coefficient like H, convection heat transfer coefficient. You know, it's changing, its Q is due to the delta T. So they put a coefficient. Then they try to experimentally determine the H. Okay, that's a purely engineering way. Okay, we know Q is related. It's not like a conduction. Conduction is actually from analytical solution. Okay, for the conduction only problem, we can actually solve it. So that's why we can determine get analytical solutions. That's why it's dt over dx. It's a derivative in there, right? It's more like an analytical solution. For the convection, it's too complicated. It's flow dictated. So the flow is so complicated. You cannot solve the flow equation that easily. So then it's too complicated. You don't have the equation for convection. That's why people create this equation. Engineers create this equation. They know the Q is related to the delta T, to temperature differences, right? So why not we just put a coefficient, H times the area. Also, I know Q is related to the area, how much the area exposed. So also related. So they know they're related to the area. They know it's related to delta T, but they don't know the exact relationship. So let's force it. Let's put in the coefficient there. So that's the equation for convection. Just want to tell you the history of the convection. So here in contact, you have millions of different type of contacts. There's no way you can get an analytical solution either. So we follow this fashion too. So let's say it's a contact coefficient. I actually forget what's exactly the name of this H. It's a thermal contact, yeah, it is called the contact coefficient, okay? It's called contact coefficient. So this is a fashion to calculate the heat transfer rate in the contact region. Okay, so in that sense, our thermal resistance, what does it look like? 1 over HC times A. Okay, I use HC as a contact coefficient. That makes sense? So let me remove those. additional notes. Okay, so that's our contact resistance. That's the new thing today. Okay, so if you see everything is multiple actually objects in contact, you might want to consider the contact resistance. Otherwise, it might lead you to some error in the measurement. It's possible. Okay, so let's come back to the question. Okay, so how do we find out look at the diagram I sent you. So T2A, T2B, is that possible we find out the temperature 2A and the temperature 2B before and after the contact region? Anybody has some idea?
Yes, sir, because you said that heat transfer is the same throughout the entire thing, so we can use the heat transfer equation to find our temperatures.
I know, yes, that's true. But how? I want a little bit more detail. So now I have an unknown T2A and a T2B. How do we find it? Now, seems like I already show you on my board here. This is the equation, right? Q equal. So this is from the beginning to the end. Okay. Do we know all the three resistance? I think we know A. Resistance A, it should be given, right? Conductivity, length, area. These are the specs, so it should be given. B should be given, right? Thermal resistance B should be given. The thermal resistance of the contact should be given too. Okay, actually, it's given in the table 2.3 in the textbook. Okay, it gives you different materials. 416 stainless steel, 304 stainless steel. 416 steel grounded with 0.001 inch brass shim, aluminum ground, copper, whatever. So it gives a list of different surfaces, different materials, and it gives you the contact resistance. Okay, 1/HC. They call 1/HC. That's another name. So it's called contact conductance. Okay, there are so many names to confuse you. Okay, so contact coefficient is HC. 1/HC is the contact conductance. Okay, so on that table. So we probably know this HC. Okay, from those tables. So then what? Then should we know T1, T3, right? So we should be able to find out the Q, right? Then what? How do we find out T2A and T2B? Now we have the Q.
We can go from T1 to T2A just by doing the Q equals KA delta
That's
T,
right.
or yeah, delta T over dx for the first plate, and then the same thing for the second plate.
That's exactly. That's the same Q. You will go through T1 to T2A. Right? That would be the same. Hold on. I turned it off my screen. Okay, yeah. So in material A, right? So that's the same Q. So then you have just RTH. I really like this form. Okay, I'm not showing the KA dt dx. Okay, it's okay if you want to insist on going the KA T delta T over delta X. Doesn't matter. It's the same as this, but I like this form. It's easy to write. Okay, is that right? Look at this equation. How many unknowns there? We have our 2A there, right? Okay, we know T1, we know resistance of material A. So go through material A, you should be able to find the ending temperature T2A because you have the same Q with the entire heat transfer when you calculate from 1 to 3, from the beginning to the end. I really want you to fully understand this. Okay, this is the most important part for so far. Okay, from beginning to here. If you understand heat transfer, you understand this. That's the proof that you understand heat transfer. Okay, this is the principle. You have the same Q. It's the heat flow inside the material. Okay, heat transfer rate. Okay. Okay, that reminds me one question. Yeah, when I watch the videos, okay, I remember a couple of you want to try to find the Q heat transfer rate through, you have a container, you have a temperature difference from during a period of time. You try to see the temperature difference m dot c delta t to see how many energy change. That's not right. This is the total energy change goes through a period of time. Okay, watt here we're talking about is energy per time. So it's the per time unit, it's not the total energy, it's the energy rate. Okay, be careful. Okay, so yeah, that part, if you integrate it over an entire time to find the total energy change, that's not the watt. Okay, be careful. Okay, come back. So any questions? Everybody agree? So now you can find out 2TA. Oh, I'm sorry, T2A. Okay. So how to find out T2B?
You would take the same Q you had before and go from T2B minus T3 over RTHC, or RTHB, sorry.
Yeah, you can go through the material B, right? Your same Q will be 2 TB minus T3 divided by RTHB. Sure. Can you also go through the contact region? Sure, you can. If you know the 2TA, then go through the contact region. 2TA, a T2A minus T2B divided by contact resistance. Right? Same thing. You can choose either B or C. If you get an A out, if you go through A first, find out the T2A, then the second step, it doesn't matter. You go through B, you should be able to find out the T2B. You go through C, you should be able to find out T2B too. Okay, so is that good? Fully understand? Okay. Let me know if you don't understand. I think it's clear enough. So, I really am an advocate for this form to calculate the heat transfer problem. Use the thermal resistance. To me, it's much easier to understand, to remember. Okay, you divide and conquer. You have the general equation, very easy. Doesn't matter conduction, convection, radiation, whatever. Doesn't matter. It's always temperature difference divided by the overall thermal resistance, no matter how many pieces there. Okay, then your next task is just go find out each thermal resistance, see if you can. Okay, so that's the process I like. I really encourage you to adopt that. Okay, it's especially for a system problem, like a very complicated system. We have so many different items. With this procedure is really easy. Okay, no matter how complicated the problem is. If you nowadays 21st century, everything is a computer, AI, people, the computer think, right? Computer do those calculations, so they do some analysis, they do some thinking. That's definitely the way they're programming it into the computer. You have to separate it into, that's basic one equation. You don't have to care about any different situation. You always that equation. Then in the detail, you have subroutines, functions to call to find all those thermal resistances. Okay, so in computer programming world, they call it object-oriented programming, right? You have all those objects programming it by other people already. You can just get used to it, call it to subroutine, call those subroutine to take those functions like each thermal resistance. You can have a library of all the thermal resistances. Then that's a very simple equation to implement it in computer. Okay, you can just delta T, whatever you input, then go to the library to get all those thermal resistances. Okay, so it's a very efficient way to remember. Okay, let's look at an example before we finish this whole chapter. I think the example is probably just exactly the same as we just talking about. Okay, let's see a real problem. Example 2.12. Okay, so you have a diameter 3 centimeter steel material. You have two pieces of this material in contact. I think it's cylinders, right? Two cylinders in contact, I guess. That's a problem. That's the material is 304 steel. Okay, each length is 10 centimeter for each material. Have ground surface and are exposed to air with the surface roughness 1 μm, micrometer, right? Oh, millimeter, micrometer, right? Yeah, 1 μm. If the surface are pressed together with a pressure at, 50 atmospheric pressure, 50 atm, and the two bar combination is exposed to an overall temperature difference of 100 degrees. Okay, calculate the axial heat flow and the temperature drop across the contact surface. So two questions. One is Q. What is Q? The second question is delta T at the contact, before and after the contact. I think that's exactly the same problem as the previous page. I just wrote it down. Okay, but this is the practical problem. Let's see how we calculate it. Okay, so I guess this is the contact region. Do you need to find out the H? The contact conductance. Okay, can you practice it? If you have a textbook, go through that table 2.3 on page 59. You want me to send you a picture of this?
Yes, please.
Okay, let me take a picture. Okay. Let me send it to you. Okay, did you see it? Okay, take a look. Based on the problem statement, so what is your 1 over HC? That's called contact conductance. Okay, it's not the contact coefficient. Okay, let's find out 1 over HC first. It's pretty obvious, right? This is not a complete table, so it's not so many of them. Give me a value. So let me repeat the problem again. So this is the 304 stainless steel. So you have two 304 right here. Oh no, you only have one 304. Let's see if that satisfies the condition. So the pressure, they pressurized for the two material, right? 50 atm. Did that satisfy the condition? Here, look at the pressure range is 40 to 70 APM for that 304 stainless steel. Okay, so I think it's in the range. Roughness, it said the roughness is what, 1 μm. Well, it said the roughness here is 1.14 μm, so that's close enough. Can we use that value to represent? So the 1 over HC here for that pressure range and for that surface roughness is 5.28. We probably need this. Okay, look at the unit, pretty long, meter square C watt. And I think it's time to the 10 to the 4. So the value actually is time 10 to the negative 4. 5.28 time 10 to the negative 4. C, this is C per watt. Okay, so that's a value from the table. Is that okay? Everybody have trouble reading this value or this table? Is that okay? That's a simple table, right? Okay. I hope we have no problem with this. Okay, so what's the question? Q? Q equals to what? I want you to write yourself. Can you please just write the equation, write that first equation I write here every time we do any problem here? Can you write this to just remind yourself you have a right direction, or maybe for your record, 10 years later, you'll come back to look at your writing here. Okay, I know what I did here, there. Okay, can you just do that? I think many of you just don't want to copy the equation. Okay, please, that's good habit for an engineer. Okay, really, seriously, always write down the equation. That's for your record.
What does that 304 refer to again?
What did you say? I'm sorry.
304 steel, what does that refer to again?
I'm not too sure of the material. That's type of the steel. Okay, anybody can answer that question? You chemical engineers, probably you guys have those metallurgy, those classes, did you? I'm not too familiar. That's just type of steel. I don't know what's the behavior of that steel. Maybe it's a common used steel, I guess. Okay. It's type of stainless steel, okay? Okay, I'm waiting on the equation. Anybody can give me the equation?
It'd be delta T on top over RTH of the first bar plus
Okay.
RTH of the second bar
Let's
plus
say
RTH
steel.
of the contact. Steel.
Okay, are they the same?
Should be, yeah.
Yeah, how about just 2 times?
That's good.
Okay, yeah, save my writing, okay. Contact, okay. Every time when you solve a problem, just write down the main equation, okay. It's not only for me to read, it's for yourself. It's a good habit, okay. Engineering calculation, always it's for your record, maybe 10 years later, people sue you, you're gonna get out and take out what you already original calculated, okay. So now, do we have everything? Okay, now I can input the values, right? Delta T is 100 degree, okay, 2 times. So thermal resistance of the steel, what's the form? It's length divided by Ka, right? Okay. If I don't directly know the value, let's just keep that way. Is a K given? I think K is given. I forgot to read.
It's not given, I don't think.
It's not given. So probably you're gonna find it from some table. It said 16.3. I think there. Anyway, that's thermal resistance of this material. 16.3 meters K. Okay. Okay. So you have Ka. Okay, 2 times. So what are the thermal resistance? 1 over HA. Okay. So I guess you should be able to find the value. L is what? L is 10 centimeter, 0.1 meter, right? K is 16.3. Okay, 1 over HC is given this value. Okay, A, area is quarter pi D square. Area is quarter pi D is 0.03 meter square, okay? So everything you know. So here you should be able to calculate the Q equals 5.52 watt. Okay. Any question on doing this? It's easy. See, you follow this process, it's easy. Thermal resistance. Okay, no question? Okay, now we need to find out the delta T in between the contact. So we are looking at the contact region only. This is the overall, right? Overall. So contact region. You can also write the equation like this, right? The same Q. Okay. The other thing I wanna see when I saw when I watch your video, your equation calculation, and also sometimes when I look at your quiz. Okay. You're not strictly follow the equation equal sign. Everything you write it down, one line or two expression, one minus the other, has to be equal to something. Okay, I see some of you just say summation, for example, summation f equals to 0. Okay, maybe this is the example in the fluid class. Force equal to 0, summation of f equal to 0. So you have two terms, two force, force 1 minus force 2. Then you stop there. You keep on calculation. Force 1 minus force 2 equal. No, force 1 minus force 2 equals to 0. Don't miss that equal to 0 part. It's very important. Okay, so equal sign. Okay, remind you. Sometimes you have to write the Q equal to something, then it equals to an expression, right? Okay. Delta TC, that's what we want to calculate, right? Before and after the contact region, right? Is that right? That's it, right? Delta T over thermal resistance of the contact region, which you already calculated here in the previous step. Okay. Then left-hand side equals to Q. Q is given, not given, you calculated 5.52 watt, right? So this, you should be able to calculate based on these two information. So your delta T C is what? 4.13 Celsius. So your temperature drop before and after the contact is 4 degrees, about 4 degrees here. The overall temperature drop in the whole material, the whole system is 100 degrees, right? Here, you have 4.13 degree temperature drop. Okay, the temperature, that actually you lost some temperature here. Okay. Again, the heat is not lost here in contact. It just slow down the transfer of the heat and then make the temperature drop more. Okay, because of how we have the contact resistance. Okay, I guess that's the example, and that's the last topic of the chapter 2. Okay, so now you have a completed picture of the convection conduction problem, especially here in this chapter, focused on the conduction at the beginning by introducing the thermal resistance idea, right? Conduction, but actually we combine it with conduction and the convection. Okay, but if you have a radiation, whatever, or other fancy heat transfer mechanism, you can always include it in this equation by adding a contact resistance. Okay, the contact resistance, like this, a lot of example is in series configuration, but it's also can do in parallel. Okay, I remember I mentioned the multiple fins problems previously, right? It's in parallel configuration, so the form is not just resistance adding together. It's same as the electrical circuits when you do the resistance for the parallel configurations. Okay, just be careful on those kind of situations. So you should be good on solving the combination heat transfer problems. Okay, with different type of mechanisms. See, this. I think that's one of the goal for introducing the thermal resistance idea, because when you calculate the conduction, convection, radiation, their equations are all different. So that will increase the complexity when you solve problems. But now you look at this equation, all the different information has been included in the contact resistance, which is a coefficient. The equation will be, overall equation will be simple. It will be always the same equation. Then it's up to you how to find out each resistance from convection, from conduction, from radiation. That will be all different. Okay, but that's individual sub-problems. Okay, it's not the overall equation is the same. Otherwise, if you don't introduce this, then your overall equation will be more complicated if you have a conduction, convection, radiation combined. Okay, so that's what I want to combine. Okay, for chapter 2. Okay, next time we will skip to chapter 3 and 4. We will directly go to chapter 5 for the convection heat transfer. Okay, very detailed convection. So it will be the convection. We'll look at the flow field. Okay, why and how those flow affect the convection heat transfer coefficient. Okay, that's the next stop. Okay.
And next video projects is the second half of chapter 2. Is that correct?
That's correct. Second
All
half of a chapter 2. Everything. It's up to you to pick. Okay, topic. Okay. So it would be due 2 weeks from today for the next project. Okay. If you don't have any other questions, that's it. And have a good
Yes,
day.
sir. Dr. Zhang, will you have any free time to talk today after like the next class or no?
Yeah, I can talk. Are you in the fluids class too?
No, sir, I'm not in fluids.
Okay, so why not send me an email? I can just try to respond back to you. Is that okay?
Okay, yes, sir. Thank you.
Yeah, you're welcome. Okay. Okay, so that's it for today. See you next time, Wednesday.